this is I omega. L equal to I omega. The angular momentum of rotational motion is I omega, where I is the moment of inertia of the particle about the axis of rotation and omega is its angular velocity. Now, how does it compare with the equation for linear momentum? You know that linear momentum P equal to mv and angular momentum L equal to I omega. I hope now you are able to appreciate the parallel nature of this. The linear momentum P equal to mass times linear velocity, angular momentum L equal to I, the moment of inertia, times angular velocity omega. So, we have now covered practically all aspects of rotational motion. For every quantity we discussed in linear motion, there is a corresponding quantity in rotational motion. We need to put all these things together to consolidate your understanding in order that we may solve problems. Let's now look at a relation between torque and angular momentum. Now tell me if you remember. In linear motion, there is a relation between linear momentum and force. Force and linear momentum. What is the relationship? Well, if you were in my class sitting in front of me, I would have given you an extra credit point if you give me that answer right away. Alright? But if you got it, give yourself a pat on the back. But if you didn't get it, pinch your earlobes. It's a very important relationship. The relation between force and momentum. Force is a measure of the rate of change of momentum. Is that right? I even told you that is the definition of force in Newton's Principia. So force in linear motion, force is a measure of the rate of change of momentum. So what do you think you would expect the relation between torque and angular momentum? You would expect the same thing, don't you? Torque should be a measure of the rate of change of angular momentum. Well, let's see whether it is true. You know that angular momentum is R cross P, is the cross product of the R vector and the P vector. Let's take the derivative of this. dl by dt, knowing that R is a constant vector, dl by dt is R cross dp by dt. Is that right? That's no problem there. But dp by dt is the net force. That's the one I just asked you. The rate of change of linear momentum is a measure of the force. So dp by dt can be replaced as F net. Therefore, dl by dt equal to R cross F net. Well, R cross F net is what we call tau, torque, isn't it? Is that the definition we just did earlier on in the part 1 of this lesson? Or this lesson? Yes. Torque is R cross F. And therefore, what do you see? Tau equal to dl over dt. Isn't that what we were looking for? Net torque is the rate of change of angular momentum. See how beautiful. The net force is the rate of change of linear momentum. The net torque is the rate of change of angular momentum. All right. Let's now talk about conservation of angular momentum. Well, if linear momentum is conserved, angular momentum also should be conserved. Now, just like linear momentum, angular momentum L is conserved. Now, let's consider a disk like this. The disk on the right has a moment of inertia I1 and it is rotating with an angular velocity omega I or omega 1. So its moment of inertia is I1 and its angular velocity is omega I or initial angular velocity. Now its angular momentum is L1I equal to I1 omega I. Is that right? Its initial angular momentum at this time is its moment of inertia I1 times its initial angular velocity L equal to I omega. L1I equal to I1 omega I. A second disk of moment of inertia I2 is shown above. Here it is. Now this has a moment of inertia I2 and it is initially at rest. Now, have you ever seen one of those old record changers? When a record is going round on a turntable and it is nearly finished, you can allow the second record to fall on it. That means the second record is initially at rest. Its angular velocity is 0. It's now going to fall on the record that is already turning. That is the situation here. So here we have the first disk rotating with an angular velocity omega I. It has an angular momentum L1I equal to I1 omega I. And here we have a second disk which is now going to be dropped onto this first disk. What is the angular momentum of this disk before dropping? L2I equal to 0. Therefore, the total momentum of these two disks now is I1 omega I, the angular momentum of this disk, plus 0 because that has no angular momentum, it is not rotating. The total angular momentum Li, initial angular momentum, is I1 omega I. Okay. If disk 2 is now allowed to fall onto disk 1, the two together now will rotate with an angular velocity omega f, so that the final angular momentum will be, can you write what the final angular momentum will be? When this disk falls onto here, the two together are going to rotate. That means the total moment of inertia now is I1 plus I2. I2 is the moment of inertia of the second disk. So the final angular momentum is therefore I1 plus I2 omega f. You see, the total angular momentum is now I1 plus I2 omega f. Now, according to the conservation of angular momentum, the total initial angular momentum must be equal to the total final angular momentum. Is that right? That means I1 omega I must be equal to I1 plus I2 omega f. Now, this has wide applications and a very, very useful relation: the conservation of angular momentum. I'm sure you have seen a skater, well, going round in circles, is that right? Spinning like this. Now, how do they do that? Now, what they do is they first keep their arms apart like this, so that they have a greater moment of inertia. You see, the moment of inertia of an object depends on its, well, remember, this is the axis of rotation if I rotate. Now, moment of inertia is mr squared. That means if my hand is over there, this part of my hand, the moment of inertia will be this mass times this r squared. So if I keep my arms outstretched, I am increasing my moment of inertia. So if I start spinning with my arms like this, I have an angular momentum. What will be my angular momentum? My angular momentum, I'm going to call it I initial, will be I omega. I'm going to call it angular momentum L initial equal to I1 omega 1. My initial angular momentum is I1 omega 1 or I sub I omega I, initial angular velocity. Now, as I keep doing this, what happens if I bring my arms close to my body? I'm reducing my moment of inertia. So when my arms are closer, my angular momentum at that time, LF, will be IF omega F. Now, the moment of inertia when my arms are close to my body will be smaller than the moment of inertia when my arms were outstretched. That means you know that the conservation of angular momentum dictates that Li must be equal to Lf. That means I omega I must be equal to IF omega F. Now this is very significant because when I bring my arms closer, my moment of inertia IF becomes smaller, and in order that the angular momentum may be conserved, my angular velocity must increase. So if I start off like this, when I bring my arms, I go very fast, and that is what these skaters actually practice. So conservation of angular momentum has great applications. Well, if you now put all these together, what have we done in this lesson? We discussed practically all quantities in rotational motion that we used in linear motion. Is that right? Torque equal to I alpha, F net equal to ma. The angular momentum L equal to I omega correspond to P equal to mv. Kinetic energy for linear motion 1/2 mv squared. For rotational motion 1/2 I omega squared. And what is the kinetic energy of a rolling object? 1/2 will be kinetic energy of rotation and the kinetic energy of translation, 1/2 mv squared plus 1/2 I omega squared. Well, so put all these things together. I'm going to do another lesson. Using all these, we will solve problems. All right, I will see you for that later on.